Imagine running your server-side JavaScript, not, 20% faster, but 1,800% faster. Like no Node.js runtime, no bun engine, no JVM, just pure mathematical logic walking a structural graph of your code.
Yeah, it completely upends how we think about executing software, honestly. Cause for decades, the industry consensus has essentially been that if you want the developer velocity of a high-level language like TypeScript or Python, you just have to accept the heavy tax of the interpreter or the virtual machine.
Right, and that tax is massive. You're dealing with JIT compilation overhead,
Yeah.
garbage collection pauses, and these multi-megabyte memory footprints just to spin up a single serverless function.
Exactly.
But the internal document we're examining today, it's a README file for a project called Gnosis Polyglot. It proposes a world where all of that machinery is simply discarded. We're looking at a structural runtime that strips away the unique engines of Python, JavaScript, Java, and just treats them all as raw mathematical topologies.
And, well, whether you're an infrastructure engineer fighting cold starts in distributed systems, or just an application developer tired of the bloat inherent in modern web frameworks, the benchmarks in this document are, they're going to challenge your baseline assumptions about what is physically possible in software execution.
So we're diving straight into the deep end of how code actually runs. Gnosis Polyglot is described as a Rust-based toolchain that handles language parsing, control flow graph extraction, CFG, and framework recognition, and the sheer scope of what it targets is staggering.
Yeah, it's wild.
It natively recognizes TypeScript and JavaScript frameworks like Express, Hano, Koa, Fastify. It handles Go frameworks like Jin, Chi, Fiber, Echo. It tackles Python's FastAPI, Flask, structural errata. It even maps Java's Spring framework.
Which is an incredibly diverse set of paradigms. Like when you look at an Express server in Node versus a Spring Boot application in Java, you are looking at fundamentally different approaches to memory management, routing, lifecycle hooks.
Yeah.
Exactly. Spring is heavily reliant on decorators, dependency injection, and this massive class-based architecture. Whereas Express is, well, it's essentially just a chain of middleware functions passing a request object down a line.
Right.
To claim you have a single tool chain that natively parses and extracts all of those disparate philosophies, it kind of implies Gnosis Polyglot is acting as a sort of universal translation layer.
It is, and the document uses a very specific term for this process. They call it lowering.
Glorying.
Yeah. So when Gnosis Polyglot processes existing framework source code, it lowers those human-readable abstractions down into what it calls GG server topologies.
Okay, I want to pause on lowering. Because in compiler theory, that usually means taking something like a for loop and turning it into assembly-level go-to instructions.
No.
But here, they're taking an entire architectural framework like an Express app's routing table and distilling it down to a topology.
Precisely. It's stripping away all the syntactic sugar and the language-specific semantics. What you are left with is just a pure graph structure.
Yeah. The document defines this graph as a collection of nodes, the edges connecting those paths, and per node IR, which is an intermediate representation of the logic at that specific point.
So like every discrete action, an if statement, a variable assignment, a database call that becomes a node, and the execution flow determines the edges connecting them.
That's it, exactly.
It's building a roadmap of the application's entire logical potential.
Yeah.
But a roadmap doesn't drive the car. You still need an engine to actually traverse that graph and execute the instructions, right?
Yes. And that brings us to the core innovation of the document, the runtime they call Monster.
Monster.
Yeah, this is a Rust native engine specifically built to execute these extracted topologies. The document states unequivocally that when Monster runs your code, there is no JavaScript engine, no Python interpreter, and no Java virtual machine involved.
See, that is the part that immediately triggered my skepticism. You can map out an abstract syntax tree or a control flow graph all day long. But actually executing that IR natively without V8 or the Python interpreter handling the dynamic typing quirks, the memory allocation, the event loop.
It sounds impossible.
Right. The source explicitly says a file just becomes a graph. And Monster simply walks that graph. It just steps from node to node.
Well, the document does mention they maintain a compatibility binary called nexec, presumably for legacy fallbacks. But the primary execution path is the direct graph traversal by Monster.
But the immediate engineering problem with taking a massive Express or FastAPI application and executing it purely as a mathematical graph is the sheer messiness of dynamic languages.
Oh, absolutely. JavaScript and Python are notorious for runtime quirks that break static analysis.
So if you bypass the native interpreter, how do you guarantee you aren't subtly altering the behavior of the application?
The developers recognize that exact vulnerability. You can't introduce a universal runtime without absolute execution fidelity. So they established what the document calls a structural pass bar, and they tested it across thousands of exported functions within their monorepo.
Let's break down that methodology because it's not a standard unit test suite.
No, not at all.
They fed real source code into Monster using a JSON input structure, and they categorized a structure failure, a structural failure, as any instance where the runtime lacked an extractor or an evaluator kernel for a specific node.
Essentially, if Monster's GraphWalker lands on a node and doesn't possess the mathematical kernel required to resolve that specific instruction, it flags a structural failure. It means the mapping is incomplete.
But the truly fascinating metric here is how they define a pass. The source explicitly notes that a pass actually includes runtime errors.
Which is brilliant when you think about the objective. Like, the goal of Monster isn't to magically fix poorly written code. The goal is perfect emulation of the structural flow. If a piece of TypeScript code was written in a way that attempts to access a property on an undefined variable, the V8 engine is going to throw a type error. For Monster to pass the structural bar, it must follow that exact same logical path and mathematically arrive at the exact same failure state.
Yeah, because if you migrate an enterprise application to a new runtime, you need the guarantee that its failure modes remain identical. If it fails differently, you've introduced behavioral drift, which is an absolute nightmare to debug.
Yeah.
Perfectly mimicking the errors is the ultimate proof of fidelity.
And the scale of their testing proves this isn't just theoretical. They hit a 100% structural pass rate across a highly varied sample size.
Wait, 100%?
100%.
Yeah.
We're talking 1,499 TypeScript functions, 100 TSX functions, 130 Python functions, 30 Java functions, and 51 Rust functions. 0 structural failures.
That's insane.
Every single path, including the error paths, executed with total structural fidelity.
If you're an engineer listening to this, you know the terror of migrating a system to a new environment and discovering that your edge case loop logic acts subtly different because of how the new compiler handles closures.
Oh, yeah.
Monster's 100% pass rate suggests you wouldn't have to rewrite a single line of your business logic. The intent of the code is perfectly preserved in the topology.
Because the language syntax is just a cosmetic wrapper around underlying computational logic. Once Gnosis Polyglot translates that wrapper into its intermediate representation, Monster doesn't care if a while loop was originally written in Java or Python. It's just iterating over an array-indexed edge path.
Which perfectly sets the stage for the performance numbers. The whole reason you undertake the monumental task of building a polyglot structural runtime is to eliminate the overhead of traditional execution models. And the benchmarks they recorded on May 1st, 2026 are genuinely hard to process at first glance.
Yeah, they set up a very straightforward, easily verifiable benchmark suite. A TypeScript hello program, just standard output printing, and a fib20 test, which calculates the 20th number in the Fibonacci sequence. It's a computationally bound recursive workload.
Perfect for testing raw CPU throughput.
Exactly. And they measured Monster against Node, Bun, and Dino.
Let's look at the baseline first. Node.js took 65.70 milliseconds to run the hello script. Bun, which is an engine built specifically from the ground up for speed, brought that down to 19.67 milliseconds. Dino clocked in at an astronomical 7,770.82 milliseconds.
Okay, we do need to asterisk that Dino number immediately.
Yeah, that's a massive outlier.
The source document goes out of its way to clarify that Dino was measured via a shared node-compatible local subprocess in their specific testing harness. They warn against using that 7,000-plus millisecond number as a tuned representation of Dino's baseline capabilities.
That's a vital caveat. Context matters, and a shared subprocess is going to bottleneck the execution wildly. But even discarding the Dino metric, we have Node at roughly 66 milliseconds and Bun at roughly 20 milliseconds. Monster ran that exact same TypeScript hello process in 3.62 milliseconds.
Let that sink in.
And on the CPU-intensive fib20 test, Node was at 67.30 milliseconds. Bun at 20.16 milliseconds. Monster executed the entire recursive sequence in 4.68 milliseconds.
It's just staggering. That is an 18.1x speedup over Node on the standard script and a 14.4x speedup on the Fibonacci computation.
Wait, let's actually think about the physics of what happens in 3.62 milliseconds.
Good idea.
The operating system has to spawn the process, the runtime has to spin up, has to ingest the code, parse the syntax, materialize the GG topology, and actually walk the nodes to output the result. Doing all of that from a cold start in under 4 milliseconds sounds like it defines the limits of process allocation.
It really does.
Usually, just the context switch from the OS to user space eats up a substantial chunk of that time.
And the authors of the document clearly anticipate that exact pushback. They explicitly state in the text that the 3.62 millisecond figure is end-to-end.
End-to-end.
Yes, it includes the process spawn, the tree sitter extraction, the direct topology materialization, the lazy AST fallback setup, the lazy per node IR decoding, and the actual Rust graph walker execution.
Which means they have ruthlessly optimized every single nanosecond of the initialization phase.
But it gets even crazier when you look at how Monster handles cross-language execution. The source details a cross-language bridge shoot-off.
Now, this is a massive pain point in modern infrastructure. If you have a Node.js API that needs to offload heavy computation to a native Rust or C++ process, you have to build a bridge.
Right.
You take your data in JavaScript, serialize it often into JSON or a buffer, send it across inter-process communication, and wait for the native process to deserialize it, compute it, serialize the answer, and send it back. And the serialization alone is a massive CPU tax. In their benchmarks, using a standard JS bridge to execute fixtures like echo, fib10, and fanout resulted in median wall times ranging from roughly 160 to 238 milliseconds.
Because of all that serialization and context switching?
But when Monster handles the cross-language execution, because it's operating purely on its unified internal graph instead of translating between distinct runtimes, its median time for those exact same cross-language tasks was around 3.4 milliseconds.
That is a 47.9x to 69.5x performance multiple over the traditional bridge.
It effectively means the penalty for polyglot architecture drops to zero. You could have a single application seamlessly weaving Python data science libraries, Java enterprise routing, and Rust cryptography together. And the execution engine wouldn't miss a beat because it never actually leaves its native mathematical topology.
It's kind of crazy when you think about it, but you can't just claim an 18x baseline speedup and a 69x bridge speedup without proving the mechanics. How do they physically achieve this? The source document outlines a meticulous 10-point architectural philosophy detailing exactly where they shaved off those tens of milliseconds.
Let's really dig into the mechanics of these 10 commandments of speed, because this is where the genius of the engineering really shines. The first point they raise is direct execution versus wasted steps. The document states, no subprocess and no orchestration JSON reparse.
Right, so in a typical polyglot toolchain, you often see modular architectures where a parser runs as a separate subprocess, outputs an AST as a massive JSON file, and then the runtime reads that file into memory.
Right.
Monster fundamentally rejects that. The polyglot extractor runs in process.
It's similar to the difference between ahead of time, or AOT, compilation and just-in-time compiling. If you are constantly serializing the architectural blueprint into a text format just to immediately parse it back into memory, you're burning CPU cycles on I/O overhead. By keeping the extraction and the topology materialization entirely in memory, they bypass the disk and the serialization bottlenecks entirely. The source does mention you can force the JSON fallback with GenXXC subprocess 1 for debugging, but the critical path avoids it.
And that avoidance of unnecessary work leads directly into their second and third major optimizations, which is the implementation of extreme architectural laziness.
Lazy evaluation is a classic optimization, but they seem to be applying it at the foundational parsing level. The source specifies a lazy evaluator AST and a lazy node IR cache.
Let's take the AST with the abstract syntax tree first. The document explicitly points out that their structured IR paths do not parse the source code. They utilize tree sitter, which is a highly efficient incremental parsing tool, but they only trigger a tree sitter AST build if a legacy byte range fallback demands it.
I want to clarify that for the listener, cause tree sitter is fantastic. It can parse code into a concrete syntax tree almost instantly as you type, which is why it's used in modern code editors for syntax highlighting.
Right, it's very fast.
But even tree sitters take some compute. What Monster's doing is extracting the logic directly into their GG topology and entirely skipping the creation of the heavy full-file syntax tree unless an error occurs, or a specific legacy module specifically requests a byte range mapping back to the exact line and character in the original source code.
Exactly. Why build a complex map of the entire city if you already know the exact coordinates of your destination?
That's a great way to put it.
And they apply the same philosophy to the node IR cache. Branch logic, loops, binding patterns, parameter names. The source notes these are initially held as undecoded JSON structures. They are only decoded upon their very first use and then recursively reused.
That's fascinating. If I have a massive enterprise API with 1,000 endpoints, a traditional runtime parses the entire file, loading all the logic into memory just in case someone hits a specific route.
Right, burning memory and CPU for nothing.
But Monster just leaves all those unhit routes as dormant JSON. The microsecond a user actually triggers a specific switch statement or a specific loop, Monster decodes that single node, caches it, and executes it. The initialization cost for the unused 99% of the application is practically zero.
Which is exactly how they hit that sub-4 millisecond cold start time. They simply aren't doing the work that other engines do up front. But the next set of optimizations, points 4, 5, 6, and 7, they move away from parsing and get deep into the physics of memory access and routing.
Right. This is where we need to talk about their indexing strategy, because it looks like they have systematically eradicated hash map lookups from the hot path. Let's look at borrowed topology indices first.
Okay, so the document states that the function named topology lookup is built once at startup as a borrowed key hash map, avoiding a linear scan per call or cloning a map.
To break that down, when a runtime needs to invoke a function, say calculate tax, it has to find where that function's logic lives in memory. A naive approach is a linear scan, where you check every function one by one until you find a match.
Which gets exponentially slower as your code base grows.
Right. A better approach is a hash map, which is fast, but dynamically allocating or cloning those maps for every invocation creates memory pressure and triggers the garbage collector. Monster builds a single, highly optimized lookup table using borrowed memory references when the process spawns, and never pays the allocation cost again.
But the real speed comes when you look at how the GG Walker actually navigates the graph. The source highlights a node index walker cursor.
Oh, this is a brilliant shift in abstraction.
It keeps the current position on the graph purely as an array index. The walker just looks at topology.nodes bracket IDX. The document specifically contrasts this with a traditional method of hashing string IDs to find the next execution step.
And the performance delta between those two operations at the CPU level is profound. When you hash a string, you are passing characters through an algorithm to generate a memory address. It requires CPU cycles. But when you use an array index, you are just doing basic pointer arithmetic.
It's instantaneous.
More importantly, it plays perfectly into how modern CPUs handle cache lines. If the nodes are stored contiguously in an array, when the CPU fetches node index 4, the hardware prefetcher automatically pulls node 5 and 6 into the L1 or L2 cache. By the time Monster needs the next step, the data is physically closer to the processor core.
Wow, yeah.
A hash map scatters that data randomly across memory, causing cache misses which force the CPU to wait hundreds of cycles to fetch the data from main RAM.
Exactly. And the document proves this wasn't an isolated trick. They applied array indexing everywhere. They list indexed route arrays for branch routing and index-keyed loop state for managing closures and iteration. They specifically note that they do not scan edge lists or probe hash maps. They have ruthlessly flattened the graph navigation into pure array traversals.
It's the computational equivalent of repaving a winding, pothole-filled dirt road into a perfectly straight, frictionless magnetic rail line. But even with the rails optimized, they still look for ways to shave off drag. Which brings us to the micro-optimizations, like trace gating.
Right, so the source states that pass tokens, which are crucial for diagnostic tracking and telemetry, are strictly gated behind a fingerprint flag. If you don't explicitly request that data, the runtime doesn't spend a single clock cycle collecting it.
But the optimization that completely blew my mind is the batched deadline guard.
Oh, it's a perfect example of looking at the holistic cost of execution, including the operating system layer.
Runtimes constantly have to check the system clock. They need to know if an operation is timed out or if a recursive loop has run away and needs to be killed. To do that, the runtime makes a system call, like instant.now in Rust, to ask the OS for the current time.
Monster does this too, but the document notes that it doesn't check the clock on every single node hop. It batches the check, only verifying the deadline every 256th hop.
And to understand why that matters, we have to talk about context switching. Your application runs on what's called user space. The operating system kernel, which manages the physical hardware clock, runs in a highly protected ring called kernel space. When your user space application asks for the time, it triggers a context switch. The CPU has to save the state of your program, pause it, jump across the security boundary into the kernel, fetch the time, jump back across the boundary, restore the program state, and resume.
It flushes the instruction pipeline.
It is an incredibly expensive operation at the microscopic level. By only doing that context switch every 256 hops instead of every single hop, you eliminate 255 context switches from the hot path.
And the source explicitly quantifies the impact of this. This single optimization saves roughly 1 millisecond on recursive workloads.
And while saving 1 millisecond sounds mathematically insignificant to a human, we have to anchor that back to the benchmarks. The entire hell runtime is 3.62 milliseconds.
Right.
If they hadn't implemented the batch deadline guard, that runtime would be closer to 4.6 milliseconds. That one trick represents an almost 30% reduction in total execution time. It is an obsessive, granular war against latency.
So we have this picture of Monster as an impossibly fast, structurally perfect mathematical graph walker. It operates entirely in memory, completely decoupled from the legacy constraints of V8 or the JVM.
But that decoupling creates a massive architectural dilemma. If Monster is purely a math engine with no native JS engine and no inherent process model, how does it interact with the physical machine?
That's the big question.
Mathematics can calculate a Fibonacci sequence in a vacuum, but real software needs to read an environment variable, write a log file to the disk, or open a network socket to an external database.
It's the classic isolation problem. How does the pure mathematical graph touch the messy reality of the host operating system? The document devotes a crucial section to this, detailing their system of shims.
Shims. Because Monster lacks an OS model or network stack natively, it intercepts any attempt to touch the host environment with a stub. The source describes these shims as recognizing the call shape, for example. It sees the topology trying to invoke a fetch command, and instead of letting it crash because V8 isn't there, the shim intercepts it and returns a placeholder.
And the architecture of these shims is governed by a very strict set of policies regarding missing capabilities. This isn't just about routing calls, it's about defining how the runtime behaves when it encounters something it cannot execute. They outline two distinct philosophies.
There is an opt-in policy controlled by an environment variable, the next permissive shims 1. If you enable this, Monster will return legacy null returns when it hits an unsupported host touch. It essentially fakes a successful interaction.
Which is absolutely necessary for the structural pass coverage testing we discussed earlier.
Oh, right.
When they were running those 1,499 TypeScript functions to prove the structural fidelity of the graph, they didn't want the runtime actually attempting to establish thousands of real database connections or write dummy files to the disk. The permissive shim allows the graph walker to receive a simulated success signal so it can continue mapping the rest of the execution path.
So it's purely diagnostic mode.
Exactly.
But the document boldly highlights the default behavior for production execution. Fail closed. If permissive shims is not explicitly turned on, any shim that lacks a real implemented backend instantly raises an X error. Unsupported. It immediately terminates with an Xcode 9 and prints a specific error message naming the missing capability.
The runtime flatly refuses to proceed. And the source text provides a very explicit, sobering rationale for why fail closed is the mandatory default. It states they're actively avoiding the silent loss anti-pattern.
This is perhaps the most important architectural takeaway from the entire document, because the examples they give of silent loss are terrifying. They describe scenarios where a permissive runtime might hand back a sham 200 OK status from a network fetch that never actually hit the wire, or a null response from a node file write command that simply dropped the data into the void instead of persisting it to disk.
And to ground how catastrophic that anti-pattern can be in the real world, the document references a specific historical cautionary tale. They call it the 2026-0413 HFT incident.
HFT referring to high-frequency trading. Let's unpack the theoretical mechanics of how silent loss destroys distributed systems, because an HFT pipeline is the perfect example. In high-frequency trading, you're executing thousands of transactions a second. The system architecture is built on absolute trust in the runtime signals.
Right.
If your trading algorithm issues a command to write a $1 million ledger update to the disk,
And the runtime lacks the file system capability, but silently fakes a success response to keep the application from crashing.
then the trading algorithm assumes the state is secure. It moves on to the next trade, utilizing capital that mathematically hasn't actually been secured. The application remains running, completely stable, CPU utilization looks perfectly normal on the dashboard, but the state of the application is completely divorced from the state of reality. You are generating ghost data.
Exactly. When an application crashes violently, it triggers alarms. Pagers go off, traffic is rerouted, engineers intervene. The service is down, but the data integrity is largely preserved because the system halted before it could corrupt the ledger.
But silent failures are insidious because they actively corrupt the ledger while telling the monitoring tools that everything is perfectly fine.
By hard-coding a strict fail-close default, Monster guarantees that it will prioritize data integrity over uptime. If it cannot physically execute a real-world side effect, it will detonate the process immediately.
So given that strict policy, the document lays out exactly what Monster can and cannot do natively right now. The fail-close list, meaning the capabilities that currently have no backend and will exit with code 9, includes native fetch, Node.fs, and F's promises for file system access, Node.net for raw networking, and dynamic module imports.
That's a significant chunk of modern I/O.
It is. But they have successfully implemented core fundamentals. The document lists process.rgv and process.env as being snapshotted at startup.log. Console.log is fully implemented and correctly writes to standard error. They've natively wired up date.now, the math library, and standard structures like sets and maps.
There are also highly specific exceptions to the fail-close rule, which the source identifies as shaped stubs. The most prominent example is the React namespace. Things like useState and useRef hooks are not fail-closed.
Which seems to contradict their integrity philosophy, right? If useRef isn't fully implemented in the Rust backend, shouldn't it throw in exit code 9?
Well, the source explains the nuance here. Modern web development relies heavily on TSX components. The structural extraction process, the tree sitter logic that builds the GG topology, literally cannot map a TSX file if those hooks aren't present.
Oh, the parsing itself fails.
Exactly. So to allow the polyglot toolchain to successfully extract React codebases, those specific shapes have to be permissively stubbed out. It's an extraction necessity, not an execution feature.
Ah, got it. They also note that Python standard library modules like OS, argparse, and JSON utilize permissive, opaque shims where member access simply chains without erroring. It allows the graph to map the topology of a Python script without crashing, though actual execution would require case-by-case backends.
What's truly impressive is the mechanical rigor behind how they enforce the fail-close policy. It's not a lazy, top-level catch-all. The document outlines 3 highly specific call sites where the policy intercepts execution.
Right, they engineered this safety harness with incredible precision. The first interception point is at bare identifiers. If your code just calls fetch globally, the runtime stops it there.
The second is at imported module methods, categorized as Kellenstent's method. This covers the pattern where an engineer imports a specific tool like a pen file from the Node.fs module and attempts to invoke it.
And the third interception site handles unbound bare identifier calls. This is for edge cases where the import wasn't statically resolvable during the lowering phase, meaning the symbol never correctly mapped to the scope.
Yep.
At every single one of these intersection points across the mathematical graph, Monster halts, verifies the capability against the host environment, and if it's missing, throws that code 9 error explicitly naming the missing feature.
It creates a paradoxically safe environment for a runtime that is built to operate with no safety limits. The execution speed is completely unthrottled, but the boundaries of what it is permitted to do are locked down with absolute certainty.
Which brings us to the grand synthesis of what this source document actually represents. We are looking at a README that outlines a fundamental shift in how we interface with computation. Gnosis Polyglot takes the fractured, tribalized world of software frameworks, Express, Spring, FastAPI, Fiber, and completely neutralizes their differences. It lowers them all into a universal, structural, intermediate representation.
It discards the V8 engines and the Java virtual machines that we have relied on for decades.
And it replaces them with Monster, a Rust runtime that walks that graph natively. By combining extreme architectural laziness, direct array index memory access, and granular micro-optimizations like batch context switches, it executes that polyglot logic up to 18 times faster than industry standards and nearly 70 times faster when crossing language boundaries.
But importantly, it proves it isn't just an academic benchmarking trick. The 100% structural pass rate and the obsessive dedication to fail-close data integrity prove this toolchain is being engineered for hostile, real-world deployment where silent failures are simply unacceptable.
It is an absolute masterclass in taking a deeply entrenched industry assumption that high-level languages require slow, bloated engines and dismantling it piece by piece from first principles. Thank you for joining us on this deep dive. Our goal is always to bypass the surface-level tech commentary and drill down into the structural mechanics of how the bleeding edge is actually built. But before you step back into your day, I want you to consider a final thought, an extrapolation drawn directly from the implications of this internal document. If a single, highly optimized Rust runtime can perfectly strip away the semantic baggage of Python, JavaScript, and Java, if it can take the unique memory models and syntax of a dozen different frameworks and reduce them all to pure mathematical nodes on a universal graph, are we rapidly approaching a threshold where the programming language you choose is entirely cosmetic? If, under the hood, all logic eventually distills into the exact same GG topology walking at the exact same sub-millisecond speed, well, will the fierce tribal language wars that have defined the last decade of software engineering finally become completely irrelevant? Keep questioning how the digital world is built. We'll see you on the next deep dive.